Hello, this is myself, Stephen, Robert, and Uditi, and our project presentation is on automotive stock price prediction. To give a little recap, our project aims to forecast stock prices for four major car companies: Tesla, Ford, Toyota, and Volkswagen. By combining historical data with external signals and political events, we're applying a mix of time series, machine learning, and deep learning models to understand what really drives stock price movements. The goal is to generate company specific and group level predictions and present our insights through an interactive dashboard that's both informative and actionable. To go a little bit more into our goals, we have several project goals that we will be focusing on. The first is to predict future stock prices by using time series forecasting models like ARIMA and Profit to predict stock prices of Tesla, Ford, Toyota, and Volkswagen. The next is to identify influential factors, determine what factors like political events, tariffs, CEO influence, and the economy significantly affect stock prices. The next is to explore external market influences like political cycles, trade policies, and public sentiment and how it affects the stock price movement. Next, we have a goal to build predictive models, which is done by developing and fine tuning multiple forecasting models for accuracy and interpretability. And finally, we have the goal of delivering individual and group level insights. We want to produce stock forecasts for each company, as well as get an idea of what the broader regional group forecast will look like in the future.
We are using four data sets, each representing stock data for Tesla, Toyota, Volkswagen, and Ford over the past 5 years. These data sets give us a good foundation to compare the historical stock performance of these major automobile companies. Each data set contains seven key columns. The date column marks the trading day in the format of month, date, and year. Price shows the closing price of the stock on that day. Open, high, and low represent the opening price, highest, and the lowest price during the trading session, respectively. Volume stands for volume traded, measured in millions. Lastly, change percentage shows the percentage change in closing prices compared to the previous trading day. With this structure, we are able to analyze daily stock movements, identify trends, and compare how these companies performed under different market conditions. Exploratory data analysis, we started by reviewing the structure of the data set. We had stock price history for Tesla, or for all our four stocks, including variables like price, open, high, low, volume, and change percent. We first clean the data by removing missing values, ensuring data integrity across all the four data sets. The data is considered a categorical ordinal variable. Price, open, high, low, change are continuous numerical variables. Volume is discrete, which we converted from millions to absolute values. Next, we performed descriptive statistics on each data set. For example, we looked at the mean, standard deviation, minimum, and maximum values of the stock prices to understand the spread. We also created histograms to show the distribution of stock prices and high prices for each company. These helped us detect patterns and whether the price data was skewed or normally distributed. To explore daily price fluctuations, we looked at the change percent column and highlighted days where the stock prices moved more than 5%, which we treated as a significant movement or volatility. Then we performed missing value analysis, found no missing data across all four companies. For outlier detection, we used box plots and identified price spikes or unusual values outside the interquartile range. Finally, we also performed feature engineering using correlation matrix. This helped us identify relationships among variables. For instance, a high positive correlation between open and close prices is expected, but it also helped us identify redundancy for any modeling steps later on.
We're applying 4 main models in this project, each with a different strength. ARIMA captures time series structure with trends and seasonality and serves as a strong statistical baseline. Profit, which was developed by Facebook, is great for handling seasonal patterns and change points automatically, which makes it flexible across companies. XGBoost, a machine learning model, will allow us to use lag features and engineered signals to model nonlinear price patterns. And LSTM, a deep learning model, is designed for sequential data and will help us learn longer-term dependencies between stock prices over time. And by comparing these models across companies, we aim to identify which method provides the most accurate and interpretable stock forecasts.
This is an example of one of our models that we worked on. It shows the XGBoost method when applied to the Toyota stock data, in which case the blue line represents the actual daily high price that we examined, and the red line indicates the predicted price of the XGBoost model trained on lagged historical data. Now what these results tell us, now we have a root mean square error of about $3.65, an MAPE of 1.42%, and an R-squared score of 0.741. Now those are pretty strong baseline results for basic XGBoost time series regression using only lag features, albeit one with some room to improve accuracy, especially when we're looking at the sharp spikes and dips. Now what we also tell here is that the predicted prices generally follow the trend of the actual prices, especially rising and falling, which suggests the model is capturing short-term temporal patterns. But it can also tell us that sometimes it lags or it overshoots on sharp movements, and it shows some spiky noise, especially where actual prices are smoother, like late December. It also shows us that the next predicted price is $184.58, which is pretty close to the final actual price, so reasonably it's good on short-term forecasting, but isn't perfect for volatility or sudden changes, all of which are common issues with basic lag time models. But as a baseline, it is pretty strong.
Our next steps will focus on completing and tuning all 4 of our models. We'll evaluate each one using metrics like MAPE and RMSE and apply time-based validation to simulate forecasting scenarios. Then we'll tune each model, for example, adjusting ARIMA parameters, grid searching for XGBoost, and using early stopping for LSTM. Interpretation will be a key step as well. We'll look at feature importance from XGBoost, decomposed forecasts from Profit, and trend alignment in LSTM. Finally, we'll create visualizations, potentially a dashboard, to display forecasts, and begin drafting our final report and presentation for the course.
This is our GitHub repo that we have used for our project. It currently has all of our reports from 591 as well as our code, and it also has our launch report from 592, and we will upload our new code and any future launch reports.
Before we wrap up, we have some additional questions that we've answered that we know some of you might have. How do you plan to decide which model to prioritize if different models perform better for different companies? We plan to compare models using both accuracy metrics like MAPE and RMSE, and also by evaluating how well the model captures key trends and turning points in the stock data. If one model consistently performs better for a specific company, we're open to using different models for different companies rather than forcing a single solution across all 4. The goal is to prioritize both predictive accuracy and interpretability for each individual case. What visualizations do we plan to create? Visualizations we consider include line charts for closing price and volume trends, histograms for price and volume distribution, box plot for outlier detection, and heat maps for feature correlations. There are also other common practices in time series forecasting and model evaluation that we can draw on, such as residual plots, which visualize differences between actual and predicted values over time, which helps identify patterns and errors that might indicate model shortcomings. Forecast versus actual plots, which are similar to the preliminary plots shown, but perhaps showing forecasts further into the future or for different periods to assess how performance changes. Cross-validation visualizations. This can be used during hyperparameter tuning or evaluation, and show performance metrics across different splits or folds. And time series decomposition plots, which for models like ARIMA that inherently handle trend and seasonality, show decomposed components of time series such as observed, trend, seasonal, and residual elements, making decomposition relevant. Finally, how else do we plan to evaluate models? Other methods we consider include symmetric mean absolute percentage error, or SMAP, which is a percentage error metric that attempts to address some issues with MAPE, particularly when actual values are close to zero. And finally, directional accuracy, which measures how often the forecast correctly predicts the direction of change, up or down, in the time series. Obviously, we have a lot of methods that we can examine in the future.